Today we're going to be doing the Dutch national flag problem from elements of the programming interviews in Python. The tool that we're going to be using to check our answers is the EPI judge, for which you can find a link in the description. So the problem statement goes as such. Write a program that takes an array A and an index I into A and rearranges the elements such that all elements less than AI, the pivot, appear first, followed by elements equal to the pivot, followed by elements greater than the pivot. So what this means is we're going to be partially sorting an array based on what the pivot is. And based on what the pivot is, we want all the numbers less than it to come first, then all the numbers equal, then all the numbers greater than. So if we're given as input some unsorted array, we want to essentially turn it into less than plus equal plus greater than. And the equal, of course, being given by our pivot index. For example, if we're given something like 2, 2, 1, 0, 1, this would return 0, 1, 2, 2, 2. Assuming that the pivot was 1. However, if the pivot was 0, then we could very well have something like 0, 2, 1, 2, 2. So any number that is beyond the pivot, it does not necessarily have to be sorted. A really easy way to do this is to just sort all of A and not worry about the rest of the time complexity. This would, of course, work and pass our EPI judge. However, we can surely do better. So one other particular solution, which is also not the most efficient, is we could allocate some extra space for this less than, equal, or greater than array, and then combine the results after, which would give us O of n time complexity. So the way we do this is first by extracting the pivot, by using our pivot index. Then we would define each of the arrays for the subsections. So we can say less than equals empty, equal equals empty, greater than equals empty, and then we can iterate over every element of the array A. So for A in A, we check if A is less than the pivot, then we append it to less than. Otherwise, we check if it's equal to the pivot, and we append it to our equal array. Otherwise, we know that it must be greater than, so we append it to our greater than array. Now, note that we don't have a return value for this array, so we must, after allocating these three subarrays, we have to put them back into A, so we have to iterate over A again. Except this time we have to do it by index because we'll have to replace every index one by one. So there's no real elegant way to do this other than to just pop through the lists. There's many ways to do this, but here's a simple one. So we check if we have anything in our less than array, and then if we have something in our less than, then we set AI to equal whatever the last element of that array is. And we can do this because we don't care about the order of the less than array. All we care about is the fact that every element in the less than array is less than the pivot. So otherwise we can check if there's any numbers in the equal array, and then append them to, or not append them, replace them with whatever was in AI before that. Otherwise, we add it to the greater than array. Now let's check that. And that passes our test too. However, you could notice that the average time for our cases was even slower than the sorting. And despite the fact that we do have better time complexity here, so right now we have O of n, we have O of n time complexity, and we have O of n space complexity. However, it ended up being much faster than just sorting it using the built-in Python function, which is O of log n. So a.sort was O of n log n. However, it ended up being faster because the Python implementation of the sort is quite efficient, so we end up doing much better in this one. We can check again and see that it was only 14 microseconds, and the total runtime was 2 milliseconds. So we could obviously do better, and the trick here is to think about another type of sort that we could do, which is quicksort. However, instead of sorting the array completely, we use the partition part of quicksorting to just do a partial sort of the array. So if you recall, in quicksort, we choose a pivot, then we divide the array into two halves. So one side which is less than the pivot, and then one side which is greater than the pivot, which is very similar to what we're doing here. However, we also want to add an extra little nuance, which says if it's equal to the pivot, we want to make sure that it's in between. So it's very similar, but we're going to have to do some modifications. So the way we can do this is, instead of having one index keeping track of where we are in the array, we keep 3. So we're going to have an index for the array, the section of it which is less than. So elements that are less than the pivot. Then we're going to have a section which is equal to the pivot. And then we're also going to have a section which is greater than the pivot. So in our final state, the index for equal and the index for greater than are going to be the same. So if 0 to less than is everything that is less, everything from less than to equal is elements that are equal, then greater than to the end would be elements that are greater than. However, when we begin this, we're going to have another subarray which is hidden in between, which is all numbers that we have not yet processed. So everything between equal and greater than are going to be unknown. So using this strategy, we can begin. We can say less than, equal are both 0, and we can say greater than is the length of A. And if we're going to be following our diagram here, it'll actually be the length of A, because if we set it to the length of A minus 1, then that would imply that our last element is already sorted, which is not. So we're going to have to be careful with some out of bounds errors. And if we do get those errors, we can just take a look at this greater than, because that's typically what will give us trouble. So we're going to be finished our quick sort like algorithm once unknown is none. So once unknown has no elements, we're going to say while equal is less than greater than, we're going to check if the element at equal is less than A of less than, or if we're going to check if it's less than the pivot. So if it's less than the pivot, that means we have to add it to this subarray. So we say A of less than A of equal equals A of equal A of less than. And this is essentially a shorthand for swapping. This is something that we're allowed to do in Python. In a language like Java or C++, you would have to create either a temp variable or do another, or add another external function that would swap to array elements. But in Python, this is perfectly valid. So after we've swapped the elements, we're going to increment our less than counter, and we're going to increment our equal index, simply because all of these elements are going to be shifted over by 1. So otherwise, we're going to check if A is equal to the pivot. If it is equal to the pivot, that means we have to, if it's equal, then that means we don't have to do anything, because we're already in, we're just going to extend the equals array. So we do nothing. Otherwise, we know it must be greater than, since we've already checked for less than and equals. So if it's greater than, we have to recall that we need to touch this index before we do a swap. So we subtract the index, and then we do the same swap. We do A greater than A equals A equal A greater than. Then we let this run until our unknown array becomes empty, and then we return. So let's double check our work here. We check that we start with less than equal as 0 and greater than to be the length of A, which means all of our elements are currently unknown. Then we loop until this subarray is fully empty. So for each element, we start from left to right using the equal as our iterator. And then we check. If it's less than the pivot, we increment the size of our less than array and shift over our equal array. If it's equal, then we simply extend our equal array. If it's greater than, however, we have to extend our greater than array and then swap it with the value at equal. And notice that after decrementing this index, the value at this index will be greater than, because we know that it must be greater than because it hit this loop. So after each iteration, we make sure that all of these assumptions are indeed true. And then if we run this, we end up, oh, because we didn't define our pivot. So if we do define our pivot, then what we get is quite a fast runtime. And notice it's still slower than just sorting the function. But this is, of course, because the sort function is quite efficient. It's implemented with low-level techniques, and what we're looking for here is a faster time complexity. So right now we have O of n time, because we're only doing one pass on the array, and we're doing O of 1 space because we're only storing 4 other values. We're storing pivot, we're storing less than, we're storing equal, and we're storing greater than. And then we're doing everything in place. So knowing that, we know that if this array A was sufficiently large, then sorting it using the built-in function would eventually be slower. And with that, we conclude the Dutch national flag problem.